Hi, in this video we'll examine the forces which can act on an oscillating spring mass system. First, let's see the actual video of the motion of the mass attached to a spring and released from rest. As you can see, the mass moves in an oscillating motion, forming a sort of ellipse shape as it rises and falls. In this way, its x and y positions vary constantly, as can be seen in the table on the right-hand side of the screen. In analyzing this motion, we can start with Newton's second law and find that the object's net force is comprised of a gravity force equal to mg and a spring force equal to negative ks L hat. We are told that the mass of the object attached to the spring is 0.402 kilograms, and we know that g is equal to 9.8 meters per second squared. We can solve for our spring force first by finding our spring constant. We can do this by rearranging the formula for t, our period of oscillation, to isolate k. We can find t from our plot generated by Tracker, which yielded a period of 1.646 seconds. Plugging this in, we get a spring constant of 5.858 newtons per meter. We can then operate under the assumption that our net force is equal to 0 and rearrange its components to solve for our spring relaxed length, using the fact that we were given its stretched length as 0.7 meters. We found that the relaxed spring length was 0.0277 meters. We can now plug in our gravity and spring force formulas as well as their variables into VPython to generate the idealized motion of our spring, with the black arrow representing our gravity force and the blue arrow representing the spring force. As can be seen, the gravity force remains constant as the mass of the object does not vary, and the spring force changes constantly as its length shortens and elongates. The plot to the right shows the period of oscillation of the object's motion. We can then factor in the energy principle to account for the various energy components acting on our object during its oscillation. We're assuming that our system is the object, the Earth, and the spring, meaning that there is no external work being done to the object, rendering the change in the system's energy equal to 0. We can surmise that the kinetic energy and both the gravitational and spring potential energy make up the total change in energy. We can now plug in the formulas for these components, shown here, into VPython to show the object's total change in energy. The plot to the right side of the screen shows the blue line as our delta K, the red line as our delta U sub S, the green line as our delta U sub G, and the yellow line as our total change in energy. As you can see, the change in gravitational potential energy increases as the change in spring potential energy decreases, and vice versa. As was expected, the total change in energy remained equal to 0, with all its components balancing each other out, confirming that energy was conserved in our system and that the energy principle is satisfied. We can now compare the expected motion of the object with the actual motion, with data yielded from Tracker. The blue line shows the expected motion, while the red line shows the actual motion. The actual motion was taken at a much slower time interval, which may account for the discrepancy in lines, as well as the fact that our expected motion did not account for dissipating energy, such as drag force. We can now compare the periods of oscillation yielded from the x and y components of the object's motion. As can be seen from the plots generated by Tracker shown here, the periods appear slightly different, and when calculated the periods are different, with the x period being 1.65 seconds and the y period being 1.52 seconds. This difference could be attributed to the x component consisting of a y pendulum motion, while the y component consisted of a vertical spring motion. In conclusion, we can confirm that the energy principle was satisfied in our experiment, and that the VPython models showed the force components fairly well, with the exception of the predicted and actual motions, which could be attributed to the differing time intervals and the fact that dissipating energy was not accounted for in our predicted model. Thanks for watching!